Yeah, the question is about how the substitution model of evaluation works with functions. And you're right, that's a good point. It's a little hand-wavy. And the reason it's hand-wavy at this moment is that we don't know how to write down a function other than by writing down its name. So for now, you can think about it by saying, well, wherever it says f in the body of sum, imagine that it says square. So that would be square of a. And that actually does work, thinking in those terms. You get the right answer. We'll see in just a few minutes, actually, what else it is that you can substitute in there that's the value of square. Because you were paying attention last week when I said, first we find the values of the arguments, and it's the actual argument values that get substituted in. So what's the actual argument value corresponding to the expression square? And we'll see that in just a moment. OK, other questions? Yes? Did I have to define f? No. F is a formal parameter. Remember last week I said there's three different things that are sort of arguments, and when I have to be really careful, I will be. This is one of those times. F is a formal parameter. That means it's the name of an argument. So think a minute about the other formal parameters, a and b. When I called sum square or sum cube, I said, for example, sum square 3, 7. And because I said that, in the body of sum square, a had the value 3 and b had the value 7, right? And I didn't have to say define a3. It's the same with f. And I don't have to say define f anything, because f is a formal parameter. And when we call sum, we have to give it a particular argument function. Square I defined 2 lines up. So square I did define. But I don't have to say define f. Okay? But you're getting at a good question, which is, why do I have to define square? The function I want is times AA. Why can't I just say that? That's a very good question, which is what we're going to get to next. So let me make sure there aren't any earlier questions to deal with first. Yes? OK, that's the same. All right, so let's go ahead and do that. Sum times AA 3 to 7. I get error unbound variable a. That's because, remember last week we said scheme uses applicative order evaluation, which means first thing we do is evaluate the sub-expressions in the call. So I evaluate sum by, it's a variable, I look up its value is the sum procedure. And then I try to evaluate times AA. In order to do that, I have to evaluate a. I look up a, there's no answer, because a has a value inside the procedure by substitution, but it doesn't have a value outside the procedure, which is where we're starting. So you can't just say times AA. And even if you could, let's suppose a had the value 3. Then we would in effect be saying sum 9, 3, 7. Right? So if that worked at all, we would always be adding 9. We would do 9 plus 9 plus 9 plus 9 plus 9. That's not what we want. Okay, so inside square, it's not good enough to know the square of a particular number. We have to know what function it is that we're trying to compute for each of the values. Okay? There is a way to do that. We'll get to it as soon as I make sure there aren't any other questions again. But yes? What if you have a function with no arguments? In this example, the domain of sum is functions of one argument. Okay? It doesn't make sense to say add up the values f of I unless f is the kind of function that takes one argument. Okay? We'll see later on that sometimes it's useful to have functions of 2 arguments. You know, and you could have a function of 0 arguments. It's less clear when that's useful, but we'll actually later in the course see some places where even that turns out to be useful. But in this example, and this gets back to what I was saying about domain and range, the domain of sum is functions of 1 argument, number. Okay? So what would happen, what would go wrong is inside the body of sum, when we try to do f of a, and f is a function of no arguments or 2 arguments, we get an error message, wrong number of arguments. It's important to note here that your high school math teacher was actually very sloppy in describing functions. So, and the people who wrote your high school math book and everything. So you'll see a lot, people say the function x squared, or something like that, or x squared plus 3x plus 7, whatever. There's no such function. X squared is a number. And if we know what x is, then we know what number it is. If we don't know what x is, we don't know what number it is. But in either case, it's a number. There is a way correctly to say this. And if you look in college math texts, at least the kind that are written for math majors, you will see the following notation. X maps to x squared. Okay? This symbol here is pronounced maps to. So this is the formal parameter, and this is the body of a function. Now, the reason we need to use this notation and not just say x squared, first of all, it's ambiguous because maybe you mean a number because, you know, we've solved some equation. We got x equals 43, and now x squared is just whatever 43 squared is. But besides that, consider this function. The function a maps to ax squared. What kind of function is this? Linear or quadratic? Linear is the answer, because the argument is a, and this expression is a times something that isn't an argument. So whatever x squared is, it's a number, it's constant. So this is a times a constant. Unlike the function, which is what they usually mean when they write ax squared in your high school algebra book. Right? So these are 2 different functions. And in high school math books, there's this complicated convention about how you know whether some letter that you're looking at is meant to be the formal parameter or is meant to be a constant that we're parameterizing that we don't really know what it is right now. But if you want to be formally correct, you actually put down what's it a function of. So we can do the same thing in scheme. Scheme, you should know, is a dialect of Lisp. Lisp it stands for list processing. It is there have been thousands of programming languages over the years, and most of them come and go. And you know, there aren't thousands of programming languages people still use. Lisp is the 2nd oldest language after Fortran that's still in use, some 60-odd years after it was invented. And you're about to see the thing in Lisp that makes it so have such longevity, because it's so useful. And that is the ability to talk about a function using the equivalent to that maps to notation. The notation is actually a little unpleasant. It's this. Say sum lambda of x times xx from 3 to 7. Okay? So if I just type lambda x times xx, I get this ugly thing that you can't actually type into Scheme, but Scheme will print out at you, which is its internal representation for procedures. But in terms of the substitution model, what you asked before, the thing to think of as what's going on is it's this lambda expression that gets substituted in, okay, into the body of the procedure. Okay, so why is it lambda? Because back before I was born, let alone you, a mathematician named Alonzo Church invented something called lambda calculus.